Hello everyone, I'm Sebastian Y and this is Managerial Economics. In this set of videos, I'm going to discuss the basic oligopoly models, the Cournot model, and the Bertrand model. I'm going to be using our basic game theory concepts throughout these videos, so make sure you're feeling comfortable with those before moving on. In this video, I'm going to introduce the concept of oligopoly and discuss the Cournot model. An oligopoly is a market with a small number of firms which are large relative to the total industry. There is more than one firm, but there are not enough firms to become perfectly competitive. This means the firms are going to have some degree of market power, but not as much as a monopoly would. Like monopolies, oligopolies have barriers to entry to prevent new firms from entering the market, even in the long run. The firms may or may not produce differentiated products. When dealing with differentiated products, the math does get a bit complex, so we are going to focus on oligopolies where the firms produce homogeneous products. The key difference between oligopolies and the other market structures we've studied is that firms behave strategically. That means we are going to need game theory to analyze these markets. Firms within an oligopoly understand that their actions have an impact on the other firms and that the other firms' actions have an impact on them. In a monopoly, this is not an issue because there is only one firm, and in perfect competition, each individual firm is so small that their actions alone don't have an impact on the other firms. We're going to start out by thinking about the simplest type of oligopoly, which is a duopoly. A duopoly is an oligopoly that has exactly two firms. Since duopolies involve the simplest math, that's where our starting point is going to be. But the lessons that we learn can be applied to oligopolies with more firms than that. There are many examples of duopolies we can look at in real life, or at least markets that are very close to duopolies. This includes operating systems with Windows and Mac, mobile phone operating systems with Android and iOS, and microprocessors, which are dominated by Intel and AMD. Some examples of oligopolies that are not duopolies would be movie studios. The top 10 movie studios control over 90% of the market. Soft drinks, where the market is dominated by the three largest firms, Coca-Cola, Pepsi, and Dr. Pepper Snapple, with some other firms operating on the fringes. And airlines, where concentration varies by route. Some are near monopolies and others are more competitive, but the four major airlines dominate the market in the United States. Before moving on, it's important to discuss the main assumption that we have to make in an oligopoly model. And this is whether firms choose quantities or choose prices. We never had to make this distinction before, because in perfect competition, price is determined by the market, and firms only choose quantity. In monopolies, we can frame the profit maximization problem as either a quantity setting problem, which is what we ended up doing, or a price setting problem. But since they're the only firm in the market, it doesn't actually matter which one we pick, we'll get the same answer. In oligopolies, it's an important decision to make because it fundamentally alters how the market behaves. If firms choose quantities, this is what we call the Cournot model of oligopoly, then the market determines the price based on the quantities that get picked. And if firms choose price, which we call the Bertrand model, firms choose prices and then the rules of the market determine the quantities that each sell. Which of these is more appropriate depends on the exact market that we're looking at. For example, in the airline industry, choosing quantity is probably more appropriate, because firms select the planes that are flying on a certain route well in advance, and then they price the tickets accordingly so that they fill all the seats. On the other hand, a price-setting model might be more appropriate for a consumer good like electronics, where firms might set the price and then produce enough output to fulfill the demand that comes from that. Throughout these videos, we are going to analyze both the Cournot and Bertrand model and discuss the differences. The last thing that I want to point out before we jump into the models themselves is that we are going to continue assuming, as we did in our discussion of advanced pricing strategies, that cost functions are linear. That is, the cost function for a given firm, C of Q, is going to be just C times Q, where this lowercase c is just a constant number, like 5 or 10 or something like that. Notice that we're also assuming that there is no fixed cost. When we have a linear cost function, the marginal cost is the derivative of this, which is just c, and so that's a constant marginal cost. Our marginal cost curve is going to be horizontal. And our average total cost is going to be CQ divided by Q, which is also just C. Again, the same horizontal line on the graph. This is going to greatly simplify the math that we're going to have to do so that it doesn't get in our way as we discuss the interpretation of the models and how they apply to a real-life situation. There's no reason that we couldn't do what we're going to do with a more complex cost function, but this is just going to make it a little bit simpler for us. Let's get into the Cournot model of oligopoly. The Cournot model is one of the most important foundational models in all of industrial organization and game theory. As we go through the Cournot model, you'll see that it makes a lot of intuitive sense, and it's also very flexible and extendable. We can adapt the Cournot model to encompass interesting situations beyond the basics that we go through today, including models where we can look at collusion, which we will discuss later on in the course. The Cournot model was developed in the 1830s by the French mathematician Antoine-Augustin Cournot. This was a time over 100 years before von Neumann and Morgenstern came up with the concept of game theory. But nonetheless, Cournot was doing game theory, he just didn't have the vocabulary for it yet. To start out, we need to define some terms. We are going to first deal with a Cournot duopoly. And later on, we are going to extend this to more firms, but for now we'll just look at a market with two firms. We'll call these firms Firm 1 and Firm 2. Firm 1 and Firm 2 both produce identical products to each other, and in the model, they choose their output simultaneously. And after that, the market determines what the price will have to be to sell all that output. We will let big Q be the total market quantity, and little q1 and q2 be each firm's output. Q1 is the amount produced by Firm 1, Q2 is the amount produced by Firm 2. And it must be that big Q equals the sum of the little q's. From there, we have an inverse demand function, P of Q. Once we know what big Q is, we can plug that in to our inverse demand function to determine the price. From here, I'm going to go through all the concepts in the Cournot model with an example. In our example, our two firms have the cost functions C1 of Q1. This is Firm 1's cost function, is going to be 40 Q1, and C2 of Q2 is going to be 40 Q2. So here, our two firms have identical cost functions. Later on, we'll look at what happens when they're not identical. We have a demand function, Q of P equals 320 minus 2P. Remember that the basic assumption of the Cournot model is that firms choose quantities. This means we're going to have to put the entire problem in terms of our two quantities, Q1 and Q2. We can see that our cost functions already look like that, but our demand function is Q as a function of P, and that's not going to work. This means that just like in Monopoly, the first thing that we always want to do for Cournot is to make sure that we have our inverse demand function. So we're going to take our demand function and solve it for P. To do that, I'm going to add 2P to both sides to get 2P plus Q, and I'm going to just drop the function notation at this point, equals 320. Then I'm going to subtract Q from both sides to get 2P equals 320 minus Q, and then divide both sides by 2. That's going to give me P equals 160 minus Q over 2. Don't forget to divide both terms here by 2, or whatever your coefficient is in your problem. Now I'm going to add back in our function notation over here to get our inverse demand function. We're not quite done with this yet because neither firm chooses big Q. Big Q is composed of Q1 and Q2. So I'm going to rewrite this one last time as P of Q1, Q2, it's a function of both of those things, equals 160 minus Q1 plus Q2 over 2, since big Q is the sum of the two little q's. If you want, you can multiply this out further and get 160 minus Q1 over 2 minus Q2 over 2. Again, be very careful to make sure that you're distributing the minus signs correctly. That is the number one mistake people make in working through the Cournot model. Now that we've done everything to set up the model, let's find the Nash equilibrium. Remember that the definition of a Nash equilibrium is that all the players are best responding to each other. And so we're going to have to figure out the best response functions for each firm. Essentially, a best response function is a plan of action that tells us the best quantity to choose given any quantity the other firm could potentially choose. As with all the other markets we've studied in this course, firms are maximizing profit, and so we are going to set up the profit function for each firm. Pi1 for firm 1 and pi2 for firm 2. As always, this is going to be total revenue minus total cost. Total revenue is price times quantity, where price is determined by our inverse demand function. And so we're going to get P of Q1, Q2 times Q1. That's going to be firm 1's revenue, and minus the total cost for firm 1, which is C1 of Q1. We can do the same thing for firm 2. We have our inverse demand function determining the price, but firm 2 is producing Q2, and their total cost is C2 of Q2. From here, I'm going to plug in all of the information that we have so far. So firm 1's profit, we have our inverse demand, which we solved for earlier, which is 160 minus Q1 over 2 minus Q2 over 2. We have that times Q1 minus our cost function for firm 1, which remember is 40 Q1. And then for firm 2, we have the same price, and this is always going to be the case when we have identical products. The consumers don't actually care which firm they're buying from, and so the price is going to end up being the same for both firms. We multiply by Q2 and subtract the total cost for firm 2, 40 Q2. Before moving on, I want to point out that each firm's profit, their payoff in the game, depends not only on their own quantity choice, Q1 for firm 1 and Q2 for firm 2, but it also depends on the quantity choice of the other firm. And this is because both Q1 and Q2 appear in the inverse demand function. To maximize profit, each firm selects their own quantity but does not have any control over the other quantity. So we're going to take the partial derivative of pi1 with respect to Q1, set that equal to 0 for firm 1's first order condition. We're going to do the same thing for firm 2. Take the partial derivative of pi2 with respect to Q2 and set that equal to 0. That's going to give us a system of equations that we can use to solve for the Nash equilibrium quantities. To make the calculus a little bit easier for us, I'm going to multiply everything out and collect terms. As always, this is an optional step, but I think it makes it less likely to make a mistake if you do this. Within firm 1's profit, I'm going to distribute the Q1 into the parentheses, so that's going to give me 160 Q1 minus Q1 squared over 2 minus Q1 Q2 over 2 minus 40 Q1. From there, I'm going to collect terms. 160 Q1 minus 40 Q1 is going to be 120 Q1, and then I'm going to keep everything else the same. I'll do the same thing for firm 2, and this is going to look very similar, so I'm just going to write out 120 Q2 minus Q1 Q2 over 2 minus Q2 squared over 2. Notice that these are very similar to each other. They are basically mirror images. This is because this problem is completely symmetric. The two firms are exactly the same, so we would expect them to behave very similarly. Next, we are going to take the first order conditions. First, I will do firm 1's FOC, which is the partial derivative of pi1 with respect to Q1. That's going to be 120 minus Q1. Notice that when we take the 2 down here, it cancels out with the 1/2, minus Q2 over 2, and then set that equal to 0. Next, I'm going to add Q1 to both sides, and that's going to give me Q1 equals 120 minus Q2 over 2. This is firm 1's best response function, so I'll label that BR1. To denote the best response function, I'm always going to put a star on the Q1. This tells us the best quantity for firm 1 to produce for any possible choice that firm 2 makes. We can just plug Q2 into this, and this is going to tell us what firm 1 should optimally do to maximize their profit. We will do the exact same thing for firm 2. We'll take the partial derivative of pi 2, but with respect to q2 this time, which is going to give us 120 minus q1 over 2 minus q2 equals 0. This time I'm going to add q2 to both sides to get q2 equals 120 minus q1 over 2. And this is firm 2's best response. Just like firm 1's best response function, this tells us the best q2 for firm 2 to choose for any possible value of q1. Notice again that these two functions are mirror images of each other because we have this completely symmetric problem. Note that is the case only because our two firms have the exact same cost functions. If that is not the case, then the best responses will not look so similar. Now that we know both best response functions, we can solve for the Nash equilibrium. In the Nash equilibrium, both firms need to be best responding to each other, meaning that BR1 and BR2 both need to be satisfied. This means that we're going to solve them as a system of equations. You can do this in any order you want, but what I'm going to do is take our Q2 best response function and plug that in to our firm 1 best response function. So where I see a Q2 in the first equation, I'm going to plug in the second. So I'm going to have Q1 equals 120 minus Q2 over 2. But where I see a Q2, I'm going to plug this expression right in there. So 120 minus Q1 over 2, and all of that divided by 2. From here, we need to be really careful about the algebra. There's plenty of different ways that you could go about this, but one way to do this is to multiply the entire equation by 2. But when we do that, we need to be careful that we apply it correctly. So if I multiply the whole equation by 2, on the left-hand side, I get 2q1. Then the 120 is multiplied by 2 to get 240. And then this last part of the equation is multiplied by 2, which just cancels out the 1/2. So that's going to give me minus 120 minus q1 over 2. All that's still in the parentheses. Next, I'm going to distribute the minus sign into the parentheses to get minus 120 plus q1 over 2. Again, this is a very common mistake. Make sure that you're distributing the negative sign properly. Now I'm going to collect terms by subtracting q1 over 2 from both sides, which is going to give me 3q1 over 2 over here. And then collect terms, 240 minus 120 is 120. And then to solve for q1, I'm going to multiply both sides by 2/3, which will cancel out the 3/2 on the left-hand side. And we're going to get 120 times 2/3, which is 80. To denote the Cournot-Nash equilibrium, I'm going to make a superscript Cour right there. We are almost done. Now we just need to plug the Cournot-Nash equilibrium quantity into firm 2's best response function. So that tells us that Q2 equals 120 minus Q1 over 2, and we're going to plug the 80 that we now know in there. That's going to give us 120 minus 40, which is also going to be 80. We have now found the quantities that are best responses to each other. If firm 1 is producing 80, firm 2's best response is to also choose 80. And likewise, if firm 2 is producing 80, then firm 1's best response is to produce 80. And so there's nothing either firm can do to increase their profit by changing their quantity. That's the definition of a Nash equilibrium. Let's sketch the graph for this problem. In a Cournot problem, we are going to draw graphs of the best response functions. I'm always going to put Q1 on the horizontal axis and Q2 on the vertical axis, but you could reverse those if you wanted to. I'm going to rewrite the best response function, so Q1 star equals 120 minus Q2 over 2, and Q2 star equals 120 minus Q1 over 2. For both of these, we're going to have a downward sloping line because we have a negative coefficient. So the easiest way to graph these is to find the intercepts. For firm 1, if Q2 is 0, then firm 1 is going to produce 120. Now for the Q2 intercept, we need to figure out what is the quantity that firm 2 could produce that would drop firm 1's best response down to 0. To do that, we can set 0 equals 120 minus Q2 over 2 and solve. That gives us Q2 over 2 equals 120, and so Q2 would have to be 240. I'll mark that out somewhere over here. We then draw a line. This is going to be firm 1's best response function. Next, we're going to think about firm 2's best response function. If Q1 is 0, then Q2 will be 120. And for our other intercept, we need to think about what would Q1 have to be to drop Q2 down to 0. Because of symmetry, we know that this is going to be 240 again. And then I will draw a line in between those two, and that's going to be firm 2's best response function. When you draw these, just make sure to be really careful like I just did. Make sure you understand which one is firm 1's best response and which one is firm 2's best response. The point at which these two curves cross is going to be our Nash equilibrium. And in our example, that happened at 80 and 80. Throughout this example, I've been talking about the symmetry which arises from the two firms having the exact same cost function. You can see that in the Nash equilibrium, the two firms ended up producing the exact same quantity as well. This is a general result. If both firms have the exact same cost function, they're going to end up producing the same quantity. And we can use this for a shortcut that allows us to skip some of the algebra we just did. Let's go back to firm 1's best response function, Q1 star equals 120 minus Q2 over 2. Previously, we took firm 2's best response function, substituted that in, and did some algebra to find the equilibrium. However, if we have symmetry, we know that those two are going to be the same. So we can take a shortcut and state that because of symmetry, we know that Q1 core equals Q2 core. And I'm going to define that equal quantity for both as just Q core with no subscript. So we will have Q Cournot equals 120 minus Q Cournot over 2. From here, we can just solve. So I'll add Q Cournot over 2 to both sides to get 3 Q Cournot over 2 equals 120. Multiply both sides by 2/3 to get Q Cournot equals 80. You can see that we get the exact same answer here, but again, we can only use this shortcut if the two firms are identical, meaning they have the exact same cost function. This shortcut is going to be very useful for us once we look at situations with more than two firms. The last thing we need to do is plug these quantities in to get our equilibrium price and profit. Recall that our inverse demand function was P of Q1, Q2 equals 160 minus Q1 over 2 minus Q2 over 2. From here, we just need to plug the quantities in. So our Cournot equilibrium price will be 160 minus Q1, remember, is 80 over 2, and Q2 is also 80 over 2. Again, these don't have to be the same, but they ended up being the same because the cost functions were the same. Here we end up with 160 minus 40 minus 40, and so we get a final price of 80. This ended up being the same as the quantities per firm, but that is pure coincidence in this case. Profit per firm, we'll label as pi Cournot, is going to be price times quantity, so 80 times 80, that's per firm, minus our total cost, which is 40 per unit, and we're producing 80 apiece, which is going to give us 3,200. If we want to know the profit for the entire industry, we can add up our profit for each firm, and that's going to give us 6,400. We'll keep this number in mind as we look at some more examples. That is the basic process to going through a Cournot problem from beginning to end. In the next video, we're going to extend this discussion to a few more situations.